Let's talk about the comparison theorem for improper integrals. So the comparison theorem, in summary, says that we need two functions that are continuous and non-negative on some interval. This will be the interval of integration, so a to infinity. So as long as your functions are continuous and greater than or equal to 0, then if your function is less than or equal to a convergent one, then it's convergent. If your function is greater than or equal to a divergent function, then it's divergent. Right. So for each of these situations, these are two different situations that we would use this for. They each rely on us kind of starting with an improper integral like you see here in my first example. This is like the agenda to actually determine converge, diverge. And then we want to compare our function or our integrand to one that we already know converges or diverges. So for the most part, we are using functions from the p-test. So we are going to compare to those p-test functions, which are whatever to infinity 1 over x to the p dx. So this is the first part of the p-test for the infinity case, and the rules there are that it converges if p is greater than 1, diverges for p less than or equal to 1. Okay, so let's jump into the first example and see how the comparison theorem can answer the question, converge or diverge for this interval. Now, this doesn't absolutely have to be done with the comparison theorem. This is one where you could fight through an antiderivative here, either with the arctan formula or trig substitution. But the comparison theorem saves you a ton of work because you don't ever have to do the antiderivative. Okay, so what we can do is say, well, this function, 1 over x squared plus 3, term for term is less than or equal to 1 over x squared. Right, this has the bigger denominator, so it's the smaller fraction. And I know that the integral from 1 to infinity of 1 over x squared dx converges by the p-test. So what I have is the first situation of the comparison theorem. Both my functions are continuous and positive. And I've shown that mine is less than or equal to a convergent function here. So mine must also be convergent. This is sort of like a squeeze theorem situation where my function is squeezed between the x-axis and this has finite area underneath it, so this must also. So I'm going to say this integral is convergent without having to compute any antiderivative. If the directions told me, like, if it's convergent, compute the exact value, then this theorem doesn't finish the question. Then I really would have to do the antiderivative stuff. But for converge, diverge, it's quite nice. Right, so if we say less than or equal to a function that's convergent, then we can say that we're convergent. The opposite is also true, which is what we'll see in this next example here. 1 over x minus 1. This isn't always positive, but for 2 to infinity it is, so we're still good. So we're going to take this formula 1 over x minus 1, and then think essentially like without the extras, what is this, right? So if we kind of ignore the minus 1 for a sec, this is really similar to 1 over x. So if I compare this to 1 over x, this is the bigger denominator. So this is the smaller fraction. And I know the integral from 2 to infinity of 1 over x dx is divergent by the p-test. So my function is term for term above one that's divergent. So the area under this curve is greater than or equal to infinity. So it's definitely also infinity. So we can conclude this one is divergent. Now at the bottom of the page here, I have just like a little summary of what I'm doing with these fractions. So in general, your function is bigger if it has addition with extra stuff on top or subtraction on the bottom, because the smaller denominator would be the bigger fraction. Or your function is smaller than whatever if it has subtraction on the top, because then you're just taking away, or if it has addition on the bottom, because the bigger denominator is the smaller fraction. My very last example here is an interesting one. So we have the integral from 3 to infinity, 1 over x plus x cubed dx. This is one that would be very difficult, not impossible, but difficult, would take a great deal of effort to integrate. and it's a great candidate for the comparison test. But we have to be very careful about how we apply the comparison test. Okay, so we have 1 over x plus x cubed. 1 over x plus x cubed. Okay, so both of the statements I've just written are true. So 1 over x plus x cubed is less than or equal to 1 over x, because this has addition in the denominator, so the bigger denominator is the smaller fraction. And this statement is also true, that it's less than or equal to 1 over x cubed, because again, we're adding a little bit in the denominator. The bigger denominator is the smaller fraction. Now, only one of these two statements is useful for the comparison theorem, even though they're both true. And it's the second one. So the issue with the first one is that we're saying we're less than or equal to 1 over x, but the integral of 1 over x is divergent. Less than or equal to divergent isn't helpful. We need to be less than convergent or greater than divergent. Those are the only combinations that are conclusive for this test. So saying that you're somewhere underneath infinity isn't really enough, right? But this is also true, and this guy's integral is convergent. So same bounds as the original, 1 over x cubed. This is convergent by the p-test. So now we're saying something that's useful, right? We're saying we're less than or equal to something convergent. So this must be convergent. An opposite situation would also be true. So if you can say that you are greater than or equal to something convergent, not helpful, in the same way that less than or equal to divergent isn't. So what we need for the comparison theorem is to say we're less than convergent or greater than divergent.